exam Friday 14th, same time as the class time. Midterm exam. Welcome back to NE 630 nuclear reactor physics. Last time we discussed the solution of the diffusion equation in a multiplying medium, and we showed that the solution for a bare cylinder will be cosine shaped in the horizontal, in the vertical direction, in the z direction, and will be Bessel function in the radial direction. And we showed that the geometrical buckling will be composed of two components. The first one is pi over h tilde, which will be the geometrical buckling in the z direction to the power of square plus 2.45 over r tilde to the power of a square, and this is in the radial direction. So the geometrical buckling in the cylinder will be two components. Geometrical buckling in a slab will be only one component, which will be pi over a extrapolated. If you are talking about two-dimensional slab, will be two components, pi over a extrapolated square plus pi over b extrapolated all square. If you are talking about three-dimensional slab, which in this case will be just a parallel pipe, so it will be with dimension a, b, c. It will be pi over a extrapolated all square plus pi over b extrapolated all square plus pi over c extrapolated all square. And for the sphere, it will be only on one dimension, which is the radial dimension. So now we studied the solution of the diffusion equation in non-multiplying medium. We moved forward and solved the solution, the equation, in a multiplying medium, but the reactor was bare. Then it came the time that we will see if we try to cover the bare reactor with a reflector, for example, what will be the net gain from putting a reflector. So this is the solution now for a reflector reactor. So we'll be talking about reflected reactors. So usually in case of bare reactor, and you have a slab like this, and this is the extrapolated distance here, a extrapolated, and this is a extrapolated, and this is x equal to 0. We stated that the flux would be something like this. Will be a cosine shaped flux as a function of x is equal to certain constant a multiplied by cosine bn multiplied by x, where bn is just the let's call it b1 because I did not sum over all n, is the geometrical buckling, which is just pi over a extrapolated multiplied by x. Now what will happen if we will have the same slab now, but it has the same stuff, a extrapolated, just a and minus a, and now we added a reflector to the slab here at a distance b extrapolated. So we expect, again, let's put the solution for the bare. This is phi of x for a bare reactor. What about the extrapolated reflected reactor? So in this case, this is the core here, and this is the reflector. So this is the reflector again. So core and reflector. So in the core, the diffusion equation will be exactly the same. So it will be negative dc d2 phi by dx, and this is phi and the c square plus sigma absorption in the core minus nu sigma fission in the core multiplied by the flux in the core equal to 0. So this is just the diffusion equation in the core. And in the reflector, what's the difference, do you think? What's the difference in the two equations? So negative d reflector, d2 phi reflector by dx square plus sigma absorption. What should I write the rest?
Zero.
Huh?
There's no fission.
There is no fissile material in the reflector, so this will be just sigma absorption in the reflector, phi in the reflector equal to 0. Because there is no multiplying media in the reflector. So now, what is the boundary, or what are the boundary conditions for this equation? The boundary conditions is you have to have same flux at the interface between the reflector and the core. So the flux will be phi at A from the reflector side should be equal to phi at A from the what? The core side. And this is the same here. And the second boundary condition is phi at the extrapolated distance should be equal to what? 0. So the boundary conditions are phi core at x equal to A is equal to phi reflector at x equal to A, and phi reflector at x equal to B extrapolated should be equal to 0. And what else? The current from the core at x equal to A should be equal to the current at A from the reflector equation. Yes? So, by the way, this is B extrapolated. So this should be, this is A, and this is B extrapolated. So this should be B extrapolated plus A. So I will remove this and I make it A plus B extrapolated. So this should be A plus B extrapolated equal to 0. And I will make it also to be consistent with the book. I will make it A over 2 and A over 2 and here. So just to be like the book. So this is A over 2, A over 2, and this is B over 2. So this is B extrapolated over 2. Just to be like same consistency with the book. So now you will notice that from the first equation, if you will multiply by a negative sign, you will replace the order. You will swap the order of those two terms. So it will be negative, it will be positive, will be nu sigma fission minus sigma absorption equal to 0. So this equation will be d2 phi by dx squared equal to negative something multiplied by phi, which is what? Simple harmonic motion. So it will be sine and cosine. But if you look at this equation, if you multiply by, do not multiply by anything, just take this term on the other side. So you will have d2 phi by dx squared equal to something positive multiplied by phi. So this is not a simple harmonic motion. So this will lead to e to the power of x and e to the power of minus x. So in the core will be sine and cosine, outside the core will be exponential. So we expect the solution, you will look at the solution from the core, phi core as a function of x will be some constant a core multiplied by cosine b material of the core multiplied by x, where b material of the core is just equal to what? Nu sigma fission of the core minus sigma absorption of the core divided by d of the core. This is just the material buckling from the core. So just here is the material buckling. If you multiply by negative, this will give you nu sigma fission minus sigma absorption divided by dc. So it will be by dc, and you will have d2 phi by dx square plus b square m material buckling phi equal to 0. And the material buckling is just this value here. So if you solve equation number 2, this will give you the equation number 2 for the reflector will be just equal to some constant a r in the reflector and exponential e to the power of x and e to the power of minus x. I can write them as what in a finite slab? Sine cosine hyperbolic function. So this will give me the sinh of a over 2 plus b extrapolated minus x divided over the reflector diffusion distance. So now if you look at this solution, so now the flux will be what? The flux in the reactor will be something like this. Now your flux is no longer 0 at the interface like before. When we have a bare reactor, it was 0. But now I will have something like a cosine shape. Then I will have what? Exponential shape like this. So this is the shape of the flux. But actually, this is a simplification of what's going on. The actual shape of the flux will be pretty much something like still the same. You will have a hump like this, then you will have the flux like this inside the reflector. And again, and this hump, those two ones are coming from the accumulation of the neutrons. Just there is a neutron source here, there is no neutron source here, so neutrons will come out, and this is the thermal flux. So because this is the reflector, so we'll have something like build up of the neutron, let's say up to here, then it will start decreasing again. So you'll have this hump here. This is the exact solution if you want. So we knew that if you apply the boundary conditions, which is here, flux in the core is equal to the flux in the reflector at a over 2 and at a over 2. So you take this equation, substitute x equal to x over a over 2 and x equal to a over 2 and equate them together. So you will get a function. Right hand side is cosine and left hand side is sine, for example. Then apply this differential, boundary condition. This boundary condition has what? The current. So what's the current? No, this is the total current. Total current is negative d phi by dx. Yes. So you will have d phi by dx multiplied by what? By d. So whenever you will have d phi by dx here is what? Is negative sign, and d phi by dx here is what? Is cosine. Then you will have two equations. One has cosine equal to sine, cosine multiplied by something equal to sine multiplied by something. The other equation will have what? Sine something multiplied by something is equal to cosine something. Divide those two equations, sine over cosine will give you what? 10. And sine over cosine will give you what? Hyperbolic 10. So you will obtain something like BMC, which is the material buckling, multiplied by A divided by 2 tangent of BMC multiplied by A divided by 2 is equal to D reflector multiplied by A divided by 2D core multiplied by L core multiplied by hyperbolic cotangent of B extrapolated divided by R. Why? Because when you differentiate this will give you what? Sine. This term will give you sine. But this term will give you what? Cosine. So you will have the first equation, sine equal to something here equal to cosine. And the second equation is what? Which is this one. So this is cosine multiplied by what? Sine. If you divide, this will give you what? Tangent. And this will give you what? And this is what you see here, tangent, cotangent. Okay, guys? So how to solve this equation? How to solve this equation? What do you think? How to solve x equal to e to the power of x? How to solve this equation? Huh? What's x? You will take ln here. So this will give you what? If you will take ln, so this will give you what? Equal to what? What's going on? I just replace x in one side by same x. I could not solve it. So this is called transcendental equation. How many heard about this? Transcendental equation. How many of you heard about transcendental equation before? One, only one. Okay. The transcendental equation to solve is all what you will do. You can solve it by two techniques. The first one is numerical. All what you will do, just guess a value, initial value for x, substitute, see if it gives you the same value here or not, then reiterate and do iteration until you find the correct value of x in both sides that will give the equation equal, make the equation equal. The second technique is to do graphical solution. How to do graphical solution? We will say this equation y equal to x, and this one is what? Y equal to e to the power of x. Then we will write y as a function of x. So e to the power of x at 0, e to the power of 0 is 1, so you will have something like this. This is the first function, y equal to e to the power of x. The second function, y is equal to what? X. Y is equal to x. So I will plot y equal to x, and this is the second function, y equal to x. So I have one solution here, where y1 equal to y2, and those are the solution. So this is x1, and this is x2, and those are the solution of the problem. So this is how to solve transcendental equation. This is a transcendental equation. Why? Because you have BMC multiplied by A over 2 inside the tangent, and it is outside the tangent. So if you want to bring, my solution is I'm looking for what is the value of BMC A multiplied over 2. Why? Because you knew from the criticality condition that the material buckling of the core is equal to what? The geometrical buckling of the core, which is equal to 1. I want to know why now, after I added the reflector to the reactor, what is the new material buckling and how it is equivalent to the new geometrical buckling. I know that for a slab, what's the B1 for a slab? Pi over what? This is for what? Slab, but what slab? Bare. Now I'm doing this for a reflected reactor. I want to know what's B1. So I want to calculate what's BMC. BMC is inside the tangent and it is outside the tangent. If you want to bring this downstairs here, then take tangent minus 1. So you will get BMC over 2. But oh, you got tangent minus 1 also for this side, which contain this BMA over 2. So I did not do anything. I just swapped the position. So this is transcendental equation and I have to solve it. To solve it, all what you will do is you will come to this, plot this one as y1, for example, and plot this one as y also, and see where they will cross over. Exactly like this one. And this is what we will be doing. So I will try to plot the equation now, and if you look for this equation, we will be plotting the equation with respect to B material buckling for the core multiplied by A over 2. So this is and instead of X, this is our X now. So this is our X. So how to plot the tangent of X? Just you will plot the tangent of X. Here it is. So this will be the first one at pi over 2. Then you will have another one here at 3 pi over 2, and so on. 5 pi over 2, and so on. So this is the first function. What's the second function? BMCA over 2. When I plot BMC over A over 2 as a function of BMCA over 2, will give me what? What? No, it's just a straight line. It's a constant. It's a constant. It's 1 multiplied by this. So it's a constant. So I will have the right hand side, which is this one. I will have just a constant here. So now the solution will be what? This will be this, will be this. But I am looking for which one? I am looking for the first one. So the first one, which is B material buckling for the core multiplied by A over 2, definitely it's less than what? Because this is pi over 2. This point is less than pi over 2. Yes, guys? So what you learn from here is A material buckling is less than what? It will be less than what? Pi over A. From here, you clear 2 with 2 and bring A downstairs. So B material buckling in the core will be less than or equal to pi over A. Yes? So what does it mean? I can replace for the criticality condition material buckling equal to what? Geometrical buckling. If those are equal, so the geometrical buckling will be what? Less than pi over A. What does it mean? A slab, I have the geometrical buckling for the slab is equal to what? Pi over A. Yes? Now I have a reflected reactor. I added a reflector. So the geometrical buckling, which give me the dimension of the reactor, now it became what? Less than what? Pi over A. So A is smaller than A that we got before. Yes? A is less than, you can get A here, so A will be less than pi over material buckling or pi over the geometrical buckling. So you have a smaller what? Because if you try to get it from here, what's A here? A is what? Less than what?
By
Pi over what?
B.
B1. And what's B1 in the, this is for the case of reflected. Let's say reflected. What's B1 in the non-reflected case? Pi over what? So I can remove this and I say A reflected is less than pi over A extrapolated. So pi goes by, and this would be equal to what? A extrapolated. So the A for a reflected reactor is less than A for a non-reflected reactor. And this is the gain that you get from adding a reflector to your core, that you lower or reduce the thickness of the reactor. Why? What's criticality? Number of neutrons in one generation over the previous generation. So by putting a reflector, you reduce what? You reduce leakage. So you do not need any more the same number of neutrons. So I can do what? I can reduce a little bit my what? My critical size. Okay? Okay, guys? So this is the benefit of using the reflector. So we can define now something called reflector saving. How much you save in the reflector. And reflector saving would be just what? The difference between A for the case of bare reactor and A in the case of what? So A delta is reflector saving. Your reflector saving. And delta is just equal to A for the bare reactor minus A for the reflected reactor. And if you do this calculation, this will give you 1 over the material buckling inside the core multiplied by tangent minus 1 of D core BMC divided by D in the reflector multiplied by L in the reflector, the hyperbolic tangent of P extrapolated over L R. That's it. Very simple equation. Everybody is happy. Now, when we try to do all the calculation for this chapter, what we did, we assumed that we have what? We have a homogeneous system. This is why we did not say anything about what? About cross-section is dependent, has a dependency on what? On dimension. So diffusion coefficient was constant, we get it outside. Divergence of D grad J, we took D outside the divergence term, so we do not bother. But the actual real case is we do not have a homogeneous system. We have heterogeneous reactor where you have a separate position for the fuel, separate position for the coolant, separate position for the structural material. So when you try to do homogenization to make your reactor homogeneous, and as if you get a very good blender, you are of course good reactor designer, so you will get to your nuclear reactor and get big blender and get the core and throw it in the blender, mix everything, and then get a syrup, and the other side is the core homogeneous. So this is one method. The other method is to do what? So say, okay, I will try to average my number densities using the volume fraction. So the volume fraction will be the fraction of the volume occupied by the fuel. So it is V fuel over total volume V multiplied by N fuel, and V moderator divided by total volume V multiplied by the volume, by the N number density of moderator, and so on. But what's the drawback of this method? The drawback of this method, it will not give you the correct flux. Why? Because when you have a heterogeneous reactor where you have separated fuel and moderator and so on, you have a phenomena called self-shielding. It's like the self-shielding, there is a special self-shielding and there is energy self-shielding. So I will show you what do we mean by self-shielding here for for a reactor. So what we mean by self-shielding is if you have a reactor, a fuel in the reactor like this, if you look, the fuel here inside the reactor is composed of fissile material 235, uranium oxide or whatever. Inside the fuel, what's higher? The fast neutrons or the thermal neutrons? And why? Fast neutrons. Why? Because we are producing those in fission, so they are a lot. And then they have to leave outside, get moderated, then get back to the fission and do what? And do fission again. So if we have something like measuring fast neutrons outside the core, outside the fuel, it will be something like this in the moderator. Then you will have a hump like this, because you are generating more fast neutrons inside. So now, if you are looking for the thermal neutrons, you will notice that your thermal neutrons is very high inside what? Inside the moderator. Then once you come closer and closer from the fuel, because of the absorption of the fuel, you will notice that your fast flux will not even be present in the center, maybe. If you are talking about more energetic between higher than the thermal, so maybe you will get something like this. Maybe more faster, you will get something like this, and so on. And this is why, because the first layers of the fuel will absorb the thermal neutrons a lot, because they will absorb them because of the cross-section is very, very high. And what happened? They will reduce the number of thermal neutrons inside your core. So the flux will go down, 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 until maybe all the most energetic thermal neutrons will even not penetrate inside the core. So you do not have any flux of the thermal neutrons inside your what? Inside your fuel here. So this is what we mean by self-shielding. So this is self-shielding. So if I asked you to define special, this is the special self-shielding. The energy self-shielding is similar phenomena, and let's say if you have a resonance like this, and this is the resonance, this is the cross-section, sigma as a function of energy, and this is the energy here. You will notice that the flux, your flux, will be something like this. Why? Because at low cross-section, the absorption will be what? Smaller, so the flux here will have a higher value. But once you move towards the energy of the resonance, the absorption will be higher, and then you will lower the flux, lower the flux, lower the flux, and this will be the shape of the flux 5A. This is called energy self-shielding. Energy self-shielding. So you are self-shielded by the resonance in the energy domain, but here you are self-shielded, the inside region of the fuel is self-shielded from the outside because of the high absorption of the fuel itself. So this phenomena of self-shielding, what is the effect of this self-shielding? Is changing the flux. So if you just want to homogenize, and by just multiplying, let's say sigma average for the fuel is equal to V fuel divided by V multiplied by sigma by the fuel, let's say, in the spatial direction as a function of x, this will not work. Why? Because this is just you multiply by a constant fraction. It does not take into consideration that you have a change in the flux. This homogenization here does not take into effect or into account the change of the flux because of the self-shielding, because of the lumping of the fuel. So we have to look for a right way of homogenizing the fuel and the moderator inside our reactor that takes into account this self-shielding phenomena. And this is what we will be doing now. So to do homogenization for heterogeneous fuel moderator assembly, or what you will do, usually, let's say, in actual nuclear reactors, you will have fuel assembly. So here is one fuel assembly, here another one fuel assembly, here another fuel assembly, and here another one. And maybe like in pressurized water reactor or boiling, you will have a crucified control rod that goes in between. So this is just a control rod. This is just a control rod that will control the reactor, for example. And the assembly is made of several, let's say, maybe 100 and something fuel elements in the assembly here. So, and so on. So this is fuel assembly. Each fuel assembly is composed of hundreds, maybe, of fuel elements, and there is this control rod in between the 4 assemblies, like here. So we will take one of those, and which is surrounded by moderator. So the fuel is, each one of those is a channel that the fluid will flow in, like light water. So I will take this one and magnify it. So we'll have imaginary border. This is just an imaginary border. This is not an actual border, just an imaginary border. And you have your own fuel elements here inside, and you have a water here outside. So this is the moderator or water, this is moderator, and this is your fuel, and this is just imaginary surface. And this what we call fuel cell. And of course you will have another fuel here, a 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 fuel here, which was all those. So now, again, as I told you, if you want to do sigma absorption in the fuel homogenization, you can do it as sigma absorption in the fuel multiplied by the volume of the fuel divided by volume of the fuel plus volume of the moderator, which is just over there, but this is not taken into account. The self-shielding. Self-shielding is not there. So I have to think about how to calculate a self-shielding. So I can take, this is just in cylindrical geometry. So if I am not talking about cylindrical geometry, let's assume that I'm talking about a slab geometry or something like this. So I can take a unit cell in slab geometry and try to solve it. This is in cylindrical geometry. So let's assume that I'm talking about fuel in slab geometry. Fuel in slab geometry. Now I can replace this by something like, let's assume I have, and this is the fuel. Let's say the fuel here has between negative A and A, let's say another fuel here in a slab geometry, and this is again negative A and A, so this is something like 2A, and this is the second fuel, and I have B from here to here for the moderator, so this will be B minus A. This is B to the center of the cell. Let's assume that the cell will be just this. I will have an imaginary cell like this. So fuel, moderator, moderator, like this one. So this is B from the center, this is B minus A, and this is A, which is half the fuel is A, and the moderator is B minus A. And again, I will have my flux is going like this inside the fuel, for example, and then it decreases. And of course, if you have infinite or a very large, you will expect that your flux will be constant, but because there is another fuel next to it, so you expect also to have something like this. The flux in the moderator region is maximum in between the two cells and minimum here, and this is the fuel, the flux inside the fuel. So you expect something like this. Then you have to solve the diffusion equation inside the fuel, minus d multiplied by d2 phi by dx square for the fuel, plus sigma absorption for the fuel, multiplied by phi in the fuel as a function of x equal to 0. So this is as a in the fuel. And the diffusion equation in the moderator is just d moderator d2 phi moderator by dx square moderator plus sigma absorption in the moderator multiplied by phi moderator as a function of x equal to, instead of 0, I will put a source in the moderator. Why? I am looking for the thermal neutrons, only thermal neutrons. Okay? Okay, guys? So in the moderator, there is thermal neutrons inside the moderator. So yes, so there is external source, which is those neutrons here inside the moderator. But in the fuel, there is no source of thermal neutrons. Yes? In the fuel, the only source is what? Fast neutrons. They get outside to the moderator, they become thermalized, then they will get into the moderator again. So this is why I bought a source here term in the moderator, but I did not bought any source term in the fuel. When you solve these two equations, you will get the flux in the moderator and the flux in the reflector. They will look ugly because they are ugly. So phi f and phi m, this is Sm cosine x over Lf divided by it's Lf divided by df cotangent hyperbolic A over Lf plus Lm over dm cotangent of B minus A over Lm multiplied by df over Lf multiplied by sigma absorption m multiplied by sinh B minus A over Lm. Oh, I have a cramp now. So it's ugly, as I told you. But I'm not going to write what is the phi m. You look at in the book. Look at what's phi m in the book. Why I'm doing all this mess? Okay, I solved this unit cell so that I will get the flux in the unit cell for the thermal neutrons in the fuel and also in the moderator in the unit cell. This is the unit cell in cylindrical geometry. This is the unit cell in what? In slab geometry. I want to know what's the flux in this region, what's the flux here. Why? Because if I knew what are the fluxes, I can just get a ratio of the flux inside the fuel to the moderator or moderator to the fuel, and this will give me an idea what is the self-shielding. Yes? Because if you knew, okay, the flux in the moderator is this, the flux in the fuel is this. So I can divide the flux here and I average those and I get some value, average value for the flux here. So if I divide the flux, average flux in the moderator over the average flux in the fuel, this will give me something called zeta, which is the thermal disadvantage factor. This will give me some factor for how the flux will change from the moderator to the fuel because of the self-shielding. So I can use this factor to do what? To do averaging. And this will be the correct way to do what? To do averaging. And this is the definition of the thermal disadvantage. Thermal disadvantage factor. So if I asked you in the exam to find the thermal disadvantage, you will tell me that this is Z and this phi average in the moderator over phi average in the fuel. So now you knew that your fuel goes from where to where? 0 to A, and your moderator goes from what? 0 to B, but it's not from 0 to B, it's only from B minus A to B. Yes, from B minus A to B. So I will average. So how to average? I will get the flux in the moderator as a function of x dx, and I will integrate over what? So this is the flux, and I have to integrate from A to B, the region where the moderator is, but I have to divide by what? To divide by the thickness, so that I will get an average. Yes? I have to integrate over the thickness and divide by the thickness to get an average. So what's the thickness of the moderator? B minus A. Then I have to average over the flux in the fuel as a function of x. What's the fuel? 0 to what?
A.
But I have to divide by I have to divide by the thickness of the fuel, which is what? 1. I divide by A. So 1 over this over 1 over this, A will go upstairs. And you will have, this is the formula for this. So if you do all this mess again, you will find that B minus A and A, if you multiply it, those are the thicknesses. If you multiply by a unit area in this direction, you will get volume. Yes? Thickness in this direction. This is the fuel here. The thickness of the fuel is A. The thickness of the moderator is B minus A. But if you take a slab and it has unit area in this direction, multiply unit area, which is 1 multiplied by B minus A, will give you the volume of this unit area moderator, and by A is the volume of the fuel. So you will transform this to VF multiplied by sigma A. Write it here. So the thermal disadvantage factor will be just VF multiplied by sigma absorption in the fuel divided by V moderator, sigma absorption in the moderator, all multiplied by VM, sigma absorption in the moderator divided by VF, sigma absorption in the fuel, all this multiplied by F plus E minus 1. Okay, so what's VF? The volume of the fuel is A multiplied by 1 is A. What's the volume of the moderator? Is B minus A multiplied by 1 is B unit area. And what's F? F is just A over LF multiplied by cotangent A over LF. What's E? Is nothing more than B minus A over LM multiplied by cotangent of B minus A over LM. Okay, so for certain, let's look for certain reactor geometries. So for a cylinder, V cylinder, F is equal to pi rho square F, the radius of the fuel. For a sphere, VF of a sphere will be equal to 4 over 3 pi r square F, and the volume of the moderator, V moderator, for the cylinder will be just pi rho square moderator minus pi rho square fuel, rho radius. And for the moderator, for a sphere, it's just 4 pi over 3 r square r cube moderator minus r cube fuel, r radius. But this is for a sphere, this is for moderator. So now you can calculate the effective homogeneous cross section. So sigma, let's say sigma absorption in the fuel effective. Now I can homogenize. I can take the fuel and homogenize it because of what? Because of the volume that the fuel occupy, but not only the volume that the fuel occupy, but also what? The self-shielding of the fuel I have to include. So in this case, I will say that this is the volume of the fuel multiplied by sigma absorption of the fuel multiplied by the average flux in the fuel. So I take into consideration the fact that the flux in the fuel is different, divided by sigma fuel, volume of the fuel, plus phi moderator, volume of the moderator, sigma moderator. Okay? And this is phi fuel again. When you do this, you will take sigma absorption in the fuel multiplied by V fuel divided by V fuel plus V moderator. And this is phi fuel. You take it as a common factor, phi fuel from upstairs and downstairs. And we multiplied by V fuel plus V moderator. We multiply by V fuel and V moderator up and down. And we'll divide by V fuel plus phi moderator divided by phi fuel V moderator. So this will cancel with this. And what's this? Sigma absorption in the fuel multiplied by the volume fraction of the fuel. This is just averaging just on the fact that the fuel occupies certain volume. There is nothing that includes the self-shielding. So this is what I told you from the beginning, early beginning. I can multiply the sigma absorption by the volume fraction, V fuel over volume, and this is the averaging technique. So here it is, this component. But I got another new component now. What is the other new component? Volume of the fuel plus volume of the moderator divided by volume of the fuel plus, what's this? The self disadvantage, thermal disadvantage factor. Okay, so I can take V fuel as a common factor from here and here. This will give me 1, and this will be V moderator over V fuel divided by 1 plus. This I can remove it, and I write this is the thermal disadvantage factor multiplied by V moderator over V fuel. So this is the correct way to do it. Now the correct way is to say it is sigma absorption in the fuel for the case of homogenization using just the fuel, the volume ratio multiplied by this factor, 1 plus V moderator over V fuel over 1 plus the thermal disadvantage factor multiplied by Vm over V fuel. I will stop here and continue next time. So did you get the idea?
It's homogeneous. This would be the equivalent of blending it all up.
Yeah. Homogeneous mean as you blend everything together without taking into consideration the self-shielding. Did you understand what we did during today's lecture?